all once again to this channel. Today I am going to make a video where we will try to make this turbostatic graphene. That we will use we will try to do in our VESTA software. So before starting the video, let's understand what is this turbostatic graphene. Here as you can see that this turbostatic graphene is a multi-layer graphene which has exotic electrical properties similar to those of monolayer graphene due to low interlayer interaction. Okay. Additionally, the stacking structure of the turbostatic multi-layer graphene can decrease the effect of attachment of charge impurities and surface roughness. So these are all about the charges. But what we usually understand from this, that this is nothing but a modified graphene where like you can see in this picture that where this two layers of this graphene, you see the blue layer is the lower layer, the first layer, and the upper layer is this red one. So they are rotated by certain angle theta. So here the theta value is given as 21.787, and at some point it will look like that they have joined, like they are joined through that point, but it is actually not that. So if we will see from the top surface, then it will looks like that. And here those sides, one is the green side, that is A2B1 side, and another is this yellow color side, that is A1B2 side. Okay. So this way we can try to make some structure like that. So before going to make a video on this, I will try to also enhance your knowledge about these 2D metals. So here you see that various kind of examples of these 2D metals are given over here. First one is this graphene, then HBN, and then this graphene, then perfluorographene, and then MOS2 and WSE2. Okay. So here you can see in this picture that here two layer of this graphene, they are stacked in such a way that one atom will looks like it is present over another atom. So here you can see this red color atom is present over this blue color atom, and this kind of stacking is called Bernal stacked bilayer graphene. And here in the other way, what we will see that this turbostatic bilayer, that is nothing but a twisted bilayer of graphene with relative stacking angle theta. So this theta value we know from that image that it is how much? It is 21.787, and this way we will try to do this kind of graphene. So to do all these things, here I have taken one CIA file for the graphene layer. So I am opening that using our VESTA software. So here I have opened our graphene structure. Okay, so this is our single layer graphene where we are having only two atoms. Okay, yeah, you can see that only two carbon atoms are present over here, because in the primitive graphene unit cell we are having only two carbon atoms which can make this graphene layer. And in the summary you can check this is the A and B value is same, that is 2.46 angstrom, and the C value, like the vacuum along this Z direction, is 8.68 angstrom, and this alpha beta gamma values are 90, 90 and 120 degree. Okay. So our first thing is to do this orthogonalization of this graphene so that we can make this kind of layer, this kind of Bernal stacking. So for orthogonalization I will try to use this RIPETR tool. So here I am going to use this RIPETR tool. Here there is an option to do this orthogonalization. So let's go to this orthogonalizer, and here I am going to open this file, this CIF I am going to open over here, and let's do the orthogonalized cell. Now you see that the structure is orthogonalized. Now let's download this. Okay, now this is downloaded, and I am going to this VESTA software to open that file that we have downloaded now. Okay, so this one I am opening here. So you can see that this is now orthogonalized, and this angle is now 90, 90 and 90 degree. So first thing we will try to do this is we will try to transform this unit cell. So here I am transforming this to 4 by 4 layer. Okay, and yes, search atom in the new unit cell. Okay, apply. Now this is now transformed to a 4 by 4 unit cell. Next thing is what we will do, we will try to import another, like the same file, so that we can make another layer of this. Oh shit, no. So what we will do, we can't edit our CIF file and as usual, so what I will do, I will do the undo simply. So this undo will take us to the, why this undo is, yeah, this undo will take us to the simple CIF file. Now I will export this to BAS format where we can edit our normal file. So save this file in the BAS format and open it. So I'm opening the VAS format file that I have saved now. So here we will do this transformation, edit data unit cell transform matrix to 4 by 4, like just a random number, like no such rule that you will also use 4 by 4, can take as per your requirement. Okay, apply. Now this is the file is transformed to 4 by 4 lattice. So here we will try to import the same file again, so that we can make another layer over this layer. And here we will do, like here I have clicked to C4 and here I'm going to unit cell, then transform to the same value 4 by 4 and okay, yes, search atoms. Okay, apply. Now you see that two such layers are present, but they are not visible because they are present at the same position. That's why we are seeing like single layer, but here two coordinate systems are visible. That means two atoms are present, but they are present at the same position. So for that, what we will do, we will try to, let's go to there only, click over here, and we will, now what we will do, we will try to change this coordinate of the second layer, so that we can make this Bernal kind of stacking. So I am putting the number over here. So 2.45 for A value and 2.85 for B, and along z axis we will put 2.4. So like the z axis value is nothing but the distance between two layer, just I have taken 2.4 for this time. Apply. Now you see that, so this something changed. So what is that change, that we will try to confirm with this paper what they have done and what we are doing. So here you see that, so here one atom over another, you can also see that we are also having one atom over another. I can also change the color for you guys. So the color I am going to change it to purple. Now is it visible? Like you see that the lower layer is having brown color and the upper layer is different color, and both the atoms are like putting one over another. You see that here one atom is below and this purple atom is looking up, and this way only we have stacked. Okay, now what we will do, we will try to now rotate the value, rotate these layers, so that we will get this kind of value. Okay, so to do this rotation again, what we will do, again we will go to this edit data phase. There is an option, like I'm clicking on the second layer. So here is the option where we can put our rotation value. So you know that simply coordinate geometry, that if we are having a vector that is elongated along any direction and it is making an angle theta with the x-axis, then we usually we can predict the position of that vector or position of that point as a sin theta, sorry, a cos theta and a sin theta. Okay, a cos theta is nothing but the component along x-axis, and b and a sin theta is nothing but the component along the y-axis. So similar way, simple coordinate geometry we will utilize here also. And before that, what we required is the lattice parameter of this graphene, that is nothing but 2.46. and here let's go, here I will try to do the same thing, like cos, first thing is cos theta of that angle. So that angle was 21.787. okay, this much multiplied with 2.46. We can exactly take the value of the lattice constant that was visible over here, so that we can predict our exact value. So 2.46772. So 2.4, sorry, 2.46772. Okay, so this is the value for our A. So here I am going to put this value, and this is how much, correct? Yeah, correct. Next part is to do the same thing for the sine. So here I am, so instead of cos, I will do the sine of this 21.787 multiplied with 2.46772. Okay, so sine of this value is how much? 0.91. Copy, and here paste. Okay, so this value we got for A and B value. Let's go to here, and here I will try to click on apply, then you will see the rotated values. Yeah, you see, now you tell me that whether this lattice is formed or not, and which you will tell by comparing this structure with this one. So you tell me that whether this flower kind of structure is forming or not. So see, one complete flower we have got, so the central one. So actually depending on the size of the cell, like I have transformed it to 4 by 4. You can also do the same, like you can also make it even larger, so that you can have much more of this kind of complete flowers, like this kind of complete circular things. And here we are getting one complete circle and two half circles. Okay, and if you will rotate, actually this the theta value we are using this much, maybe they have taken the right handed coordinate or left handed coordinate, that is depending on that, that's why their structure is looking like this. And you can also do the same even using different rotated options in the VESTA software. So this way you can rotate your structure and to see that whether one is over another or not. Let's go. This is also fine. Yeah, so the angle between this and this is nothing but theta, so that means we have done this upward kind of rotation. You can also do downward, a simple way, like same thing you can do, rather also you can do this 90 minus theta, then also you can put that value to make it down. I hope this will happen. Okay, so this way we have made our turbostatic graphene. Now the time is to save this. So yeah, of course, how I will save this, I will save this file to one xyz file. So let's save it. Turbo dot xyz, save. No, let me open it, whether anything happening or not, that also I need to check. Yeah, now you see that the file is saved, and this is what we were looking for. And now our file, this is our turbostatic graphene structure, and this kind of like the layer arrangement you can see it over here also. Yeah, you see this layered arrangement is happened to this graphene, and it will, from the top view it will look like this. Okay, so I think you guys are understood, like this is just an approach I was giving, that how you can do this. And also another thing, like very important thing I want to mention over here is that, so when you are doing this kind of calculation, so this moiré lattice pattern or something 2D van der Waals kind of heterostructure, so this paper I have got from the scientific report, which is published in I think 2015. So here they have given one formula, you check here this formula for this yeah, for a given bilayer with lattice mismatch delta value, the period of moiré superlattice decreases sharply with the misorientation of the angle. So this period of moiré super lattice you can calculate using this given formula. So here A is our lattice constant. For graphene it is 2.46772 that we have used, and this delta is your lattice mismatch, and this theta is that angle where you will try to rotate. So you can also utilize this formula to calculate this moiré superlattice pattern or some period of this moiré superlattice. This way you can go forward, and I will provide all the links for this paper and this paper in the video, and I hope you guys are understanding. And this way you can make any kind of structural designing of bilayer or any kind of graphene layer. And thank you all, and this much for today's session, and bye bye.